lesson of chapter 5, we're going to talk about polynomial operators. So let's start with the definition. Again, I'm not going to write these out, but you write them if you want to. But L equals A naught times capital D to the n, right? And then plus A1. All of these guys, it's called a polynomial operator when all of the A naught and A1 all the way through AN are constants now. So these are no longer functions of X, right? They're actually constants. A naught can't be 0 because if it was, then you wouldn't have dn. No. And the associated polynomial P of R is A naught times R to the power of n plus A1 times R to the power of n minus 1, blah, 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 all the way through AN. With L is equal to P of D. So this linear, this polynomial operator is just P of, if you would plug a D in there, you can see the relationship between them. Note, given polynomial operators, L1 is equal to P of D and L2 is equal to some other Q of D, right? Then the sum, L1 plus L2, is equal to P of D plus Q of D. Nice. And the composition, L1, L2, so you're doing L2 first and then doing the composition of it into L1, would be P of D of Q of D. It actually ends up being equal to Q of D of P of D, which is L2 of L1, right? So these are composition functions, or compositions, right? And they're also polynomial operators. This is rare. You know, we saw it on last chapter that in general, when you're doing composition functions, they're not always, you can't do it in any order. Oh, you can't switch the order, right? It's not normal. So this is a rare thing for this to happen, commutativity, right? But it does hold for polynomial operators. Here's the key. Here's what we're going to be ended up doing, is that y equals e to the power of rx is going to be a solution to the differential equation y prime minus r times y equals 0, which you could also write it as, remember, capital D, d to the power of 1 is like y prime. Yeah, we can replace that with a capital D and then factor out the y from each of these. And so d minus r, or d minus r of y is equal to 0. All right. Actually, before I give you that part, so I guess let's do this. Let me go back to polynomial operators. Let me remind you of these guys. This differential equation, right? Y double prime plus 5 times y prime is 5 times y prime minus 7y equals 0. Do you remember that this can be written as d squared plus 5d minus 7 of y equals 0. Do you remember that? Or P of D y equals 0, where your P of D is this guy, the d squared plus 5d minus 7. And remember, when you see that 7, you're going to just add in a little d to the 0 power, right? And then the associated polynomial of this guy is P of R is equal to R squared plus 5R minus 7. Okay, so I should have given that to you after the whole polynomial operator thing. And then the key to what we're going to be doing is that y equals e to the rx is a solution to the differential equation y prime minus r times y equals 0, which can be written as the quantity d minus r of y equals 0. All right, so let's do an example. How about y prime minus 5y equals 0, and they say solve it. Solve this differential equation. All right, well, given what this right here, this is y prime minus ry. So I can rewrite this as d minus 5 of y equals 0 now, which means my r is 5. Remember, it's d minus r. So that means the solution to the equation is y equals e to the rx, so 5x. It's like the simplest case. And we can definitely check this. Let's check it. Let's check that this equation, this solution, y equals e to the 5x, I'm claiming it's a solution to this differential equation. Well, let's see. Y prime minus 5y would be what? What would the derivative of e to the 5x be? 5e to the x. So y prime would equal 5 times e to the 5x. And then minus 5 times y was e to the 5x. And is that equal to 0? And 5e to the x minus 5e. Whoops. Typo, 5x. I don't know why I dropped that off. Sorry about that. Fix it. 5e to the 5x minus 5e to the 5x is definitely equal to 0. And so sure enough, this solution really is a solution to this differential equation. All right, I don't want to write this out. We have a theorem, so I'm going to show you this paper again. Okay, theorem says if R1, R2, and Rn are distinct real numbers, then e to the R1x and e to the R2x all the way through to e to the Rnx, so each of these distinct real numbers, right, are linearly independent solutions to the differential equation of d minus r1 times d minus r2 all the way through of d minus rn y equals 0. And the general homogeneous solution will be a linear combination of each of these guys. Y equals c1 e to the r1x plus c2 e to the r2x. So that'll be our general homogeneous solution. And note that R1, R2, all the way through Rn are solutions of the auxiliary equation. That's what they call it, the auxiliary equation of P of R equals 0. And the roots of the polynomial, and these guys are the roots of this polynomial P, which is sometimes, it's also called the auxiliary polynomial. Okay. I think this is worth writing, so let's do that. So, I'm going to write the whole thing. So here, okay. So let's go for differential equation d minus r1 and d minus r2 all the way through d minus rn y equals 0. They got to be, each of these R1, all of these R's need to be distinct, so different, right? Real numbers. Now, then the general homogeneous solution is y equals C1. I'm going to go to the next line. Is y equals C1 times e to the R1x plus C2 e to the R2x plus all the way through Cn e to the Rnx. Now where R1 through Rn are distinct real. Right. So if these guys are real, then each of these e to the R1x's are linearly independent solutions to this differential equation, and so here is your general homogeneous solution. And then note, yeah, we talked about that, about the auxiliary equation and stuff. Okay, so let's do some examples on this. All right, we want to solve the differential equation and find the general homogeneous solution. So the first one we're going to do is d plus 1, d plus minus 5. Y equals 0. All right, well, this one's an easy one, right? We're already factored out like this, yes? So that means for this guy, R would be -1. And for this one, R would be 5. And so you've got y equals C1 e to the -x plus C2 e to the 5x. That's your general homogeneous solution. Pretty straightforward. No? They don't get too much more complicated other than you're going to use your factoring skills to get some of them to look this way. Let's do another example. How about, again, solve the differential equation and give the general homogeneous solution. What's the general homogeneous solution? All right, so solve. This time we're going to do third derivative of y minus 4y prime equals 0. All right, so I'm going to change this to these capital D's, which this represents d cubed minus 4d, this is to the power of 1, of y equals 0. Those factor, a d is in common, so how about I factor out the d, and I'll have a d squared minus 4. D squared minus 4 factors. It's a difference of 2 squares, so d and d plus 2 and d minus 2. All right, that's enough. Now, our r's are, r is 0 for d, right? D plus 2 equals 0 will give me r is -2. D minus 2 will give me r is +2. And so, your general homogeneous solution would be y equals C1 e to the 0x plus C2 e to the -2x plus C3 e to the +2x. Yeah, but e to the 0 is just 1. So of course we'll simplify that to just C1 plus C2 e to the -2x plus C3 e to the 2x. Here's your general homogeneous solution to this guy. And if you worked it out, right, and you found you'd have to find the third derivative and the first derivative, and you plug those guys in, they will equal 0. They have to. That's the whole point, is for them to be for this to be a solution. Then you should be able to plug those derivatives back into the differential equation and it'll work. All right, let's do another one. This time it's solve y, the third derivative of y, right, plus 4 times y double prime minus y prime minus 4y equals 0. All right, so the first thing I'm going to do is rewrite it with the d's. This is a d cubed plus 4d squared minus d1 minus 4d y equals 0. All right, we got to factor this. I see 4 terms, so whenever I see 4 terms, I always think of, can I factor it by grouping? And so if I look at just the first two, what do they have in common? They have a d squared, so factor out a d squared, you would be left with a d plus 4. And then I look at the second two, and I need my parentheses to match, so I need a d plus 4, so I can factor out a negative, just a negative 1, right? A negative 1 times d plus, crap, this is d to the 0. This is why I need you guys live with me, huh? That was just a 4. So that was a d to the 0, because there's not a, it's just negative 4 times y. Sorry about that. There we go. D plus 4. Yeah, because that's just a non-existent thing. I'll cross it out like that. How's that? All right, so we got this y equals 0. All right. Well, now my parentheses match, so that's one of my factors. And when I factor that out, then I'm left with d squared minus 1. D squared minus 1 factors more. That's the difference of 2 squares, so d plus 1 times d minus 1. All right, fully factored into linear factors, and so now, which means they're distinct. Which word we used? Distinct. Yeah, distinct. These are real numbers and they're all distinct, right? So your r is negative 4, r is negative 1, r is positive 1. And so your general homogeneous solution would be y equals c1 times e to the negative 4x plus c2 times e to the negative x, and then plus c3 times e to the x. And obviously, if you had factored it differently from me, you should still have some constant times each of these guys, but your C1 might have been matched up with the negative x, and your C2 might have been the positive x, and maybe your C3 was the negative 4x. Like, that doesn't matter, right? These are just representing constants. So the work in between might look a little different, but I'm just looking for that. All right. Let's remember the fundamental theorem of algebra. Sounds important, doesn't it? It's because it is. The fundamental theorem. Oh my goodness. Of algebra. And I'm not going to write it out. You're going to refer to your notes. Say, the fundamental theorem of algebra states that every real polynomial, so it's a real polynomial, it's got real coefficients of degree greater than 0, it will factor into a product of real linear factors with real roots, and or a real irreducible quadratic factors, which will have non-real complex roots that will always come in conjugate pairs. So if your coefficients are real and you get a one complex answer, the complex conjugate also has to be there. Hopefully you remember that. All right, so let's do an example of this guy. D squared minus 2d plus 2. So finding the roots of p of t is equal to d squared minus 2d plus 2. So if you went to go factor that, you'd be looking for two numbers that multiply to positive 2 but add to negative 2. Not gonna happen, right? So what we'll do, we're finding roots, so we would set this guy equal to 0. I'm going to bring that constant over. I'm going to leave a little space. I'm going to leave a little space because we're going to complete the square. You also could do quadratic formula, but completing the square is pretty easy, especially with an even coefficient on D. So to complete the square, you would take negative 2 divided by 2. You get negative 1. Square it. That's a plus 1. Make sure you add it to both sides. Now that factors as a perfect square. Now, and so taking the square root of both sides, you would get plus or minus I. The square root of negative 1 is I. And then adding 1, your D is 1 plus or minus I. Yeah? Okay. So, another thing, I'll just, it's on, it is on your notes, but I'll just write it just because it's easier. Note that the real irreducible quadratic polynomial operator with complex roots, complex non-real roots, not imaginary roots, a plus bi and a minus bi, where of course b isn't 0 because otherwise they'd be real. Right? So if you know these two roots, you can always get, this follows the same thing. Do you remember the product sum rule from algebra? This follows the same thing. So the real irreducible quadratic polynomial operator with complex roots is P of D is equal to D minus the first root times D minus the second root, right? You would have done that before. And then which ends up being, when you multiply this all out, D squared minus 2AD plus A squared plus B squared. If you remember the sum product rule, it was sum product rule. It was E squared minus the sum of the two roots. Of course, we had x's back in algebra, right? But times D plus the product of the two roots. So this guy is your product, and this is 2a is the sum of a plus b and a minus b. The bi, a plus bi and a minus bi. The bi's cancel. You're left with a plus a, 2a. Where it was the minus the sum of it. Yeah, you totally did that in algebra. All right. So let's do some examples. Is my whole thing crooked? Got it lined up there. All right. So let's do a couple examples. Example 5, we're going to find the real polynomial of lowest degree. Given the roots. R1 equals 2 and R2 equals 3 plus I. All right, this is a big deal that it says that it's a real polynomial. That means it's got real coefficients, right? Well, 2 is a real root, not a problem. This guy's an imaginary root, though. It's a complex root, and they come in pairs if your coefficients are real, and these are. So we have an R3 is equal to 3 minus I. That's the complex conjugate. That's since they're real roots. All right, so our polynomial will be R minus 2 times R minus 3 plus I times R minus 3 minus I. And you can use this sum product rule for these guys, right? So I'll still have the R minus 2, but then these are my two roots, so the sum of the two roots would be 3 plus I and 3 minus I. The i's cancel, you're left with 6. The product, you got the difference of two squares. So that's a 9, first times first. Outer and inners cancel, and then a minus I squared, and if you remember, I squared is negative 1. So that's a 9 minus negative 1, which is a 10. So the sum is 6, the product is 10, which means I have R squared, minus the sum, minus 6R plus the product. And we should set these guys equal to 0 since they're roots. And that's good enough. I mean, you could multiply it through and you get a cubic, but I'm fine with you leaving it like that. Let's do another one. What if, so same thing, find the real polynomial. Lowest degree where your given roots are I and 3 with a multiplicity of 2. And hopefully you remember what multiplicity means. All right, so if it's got real coefficients, then that means if I have R1 is I, R2 is 3, we would have third root is negative I. That's the conjugate, complex conjugate, because it's like 0 plus I, so 0 minus I would be the conjugate. All right, so what does that mean? My polynomial would be R minus I times R minus negative I times R minus 3. Do you remember what the multiplicity means? You put that 2 as an exponent on the factor, not on the R, but as R minus 3 quantity squared. It means there's 2, it's like a double root, right? R minus 3, there's 2 of them there. And that would be equal 0. You want the real polynomial, so don't leave these i's. We'll do the sum product rule. So the sum would be negative I plus I. Oh, 0. Nice. Product. I times negative I, which is negative I squared, which is a negative 1, which is positive 1. All right. So this guy becomes R squared minus 0R. Don't write it. Plus 1. And then times R minus 3 quantity squared. There you go. All right, next time, so today it was they were all real roots and they were all distinct. Next time, we're going to talk about what happens when you get repeated roots. Yeah, and like that guy, and complex roots. So I set you up for like how to find, how this happens or whatever with the complex roots and all that. But we didn't actually figure out, okay, what are solutions to the differential equations when your roots are complex, non-real, or repeated. And that's what we'll do in the next lesson. All right. That's it for section 2. I hope you all have a fantabulous day. And bye.